Digital modulations are the standard for encoding data into electromagnetic waves for modern communication. In this video, I'll break down how these techniques work, explain the core types used today, and show how they are visualized using constellation diagrams. To finish, we'll move from theory to practice by building a MATLAB-compatible script using Octave. In telecommunications, modulation is the process of encoding information by altering one or more properties of a carrier wave using a modulation signal. The key properties of the carrier wave that can be modified include its amplitude, which forms the basis of amplitude modulation, its frequency, used in frequency modulation, and its phase, which is the principle behind phase modulation. In digital modulation, an analog carrier is modulated by a discrete signal. The most common digital modulation techniques are amplitude shift keying, frequency shift keying, phase shift keying, and quadrature amplitude modulation. ASK modulates the carrier wave by varying its amplitude between a finite number of states. For example, in binary ASK, a 0 can be represented by a signal with an amplitude of 0.5, while a 1 is represented by an amplitude of 1. FSK modulates the signal by switching between a finite number of frequencies. For instance, a 0 might be encoded as a signal with a frequency of 2 Hz, while a 1 is represented by a frequency of 1 Hz. PSK encodes data by varying the phase of the carrier wave. In its simplest form, binary PSK, there are two phase states shifted by 180 degrees. Finally, QAM combines both amplitude and phase modulation to encode bits, allowing for more efficient data transmission. The most common way to represent a digitally modulated signal is through a constellation diagram. This diagram visualizes the signal as a two-dimensional scatter plot in the complex plane, where the x-axis represents the in-phase component and the y-axis represents the quadrature component. For example, in this QPSK constellation diagram, all symbols have the same amplitude but differ in phase. The first symbol shifts the carrier wave's phase by 45 degrees, representing the bits 0, 0. The second symbol shifts it by 135 degrees for 0, 1. The third by 225 degrees for 1, 0. And the last by 315 degrees for 1, 1. Now let's put that theory into practice using Octave, a free alternative to MATLAB. You can also download the full code using the link in the description. We start by defining the parameters. First, we set the modulation type to ASK. Then, we choose a modulation order of 4, which will give us 4 distinct constellation states. Finally, we set the sampling frequency of the modulated signal to 100 Hz. We also need to create a symbols vector. This serves as the data we will encode. To make the visualization clear, we will generate all possible symbol states in increasing order. Next, we proceed to the constellation diagram generation. For ASK, the constellation points are simply real numbers, ranging from 1 to the modulation order, normalized to a maximum value of 1. Now let's code the PSK. This constellation is generated using complex exponentials to calculate 4 phase shifts separated by 90 degrees. Before adding more complex types, we will create a constellation plot and run the code. Let's also try PSK option. As you can see, 4 points are visible on both figures. On the left, only the amplitude varies for ASK. On the right, the amplitude is constant, but the phase changes for PSK. Now we'll add QAM constellation generation. To do this, we define the points based on modulation order and arrange them into a square using the mesh grid function. We then combine the I and Q values to create the final result and normalize the energy to 1. I will explain the math behind these steps in more detail in a dedicated video later in this course. The code is ready. Let's change the modulation type to QAM, increase the order to 16, and run the script. As expected, the plot shows 16 points arranged in a square, exactly as you would see in a standard 16 QAM constellation. In the next section, we will actually modulate a carrier wave. We use the constellation as a codebook to map the symbols we want to transmit to their dedicated states. We also need to upsample this vector to match the sampling frequency. Now we are ready to modulate. We create a time vector of 16 seconds, giving us 1 second for each symbol. We generate the carrier components for both the I and Q values and modulate the signal using these carriers. This process will be explained in more detail in the next episode of this course. Finally, we plot the signal ready for transmission. As you can see in the figure, both the amplitude and the phase are changing over time according to the specific constellation points we generated. In the last part of the video, we will look at FSK. We start by changing the modulation type and setting the modulation order to 2, which makes it easy to observe the frequency changes. Since constellation diagrams are primarily designed to show changes in amplitude and phase, they aren't the right tool for visualizing frequency shifts. Because of that, we'll implement the FSK functionality directly within the modulation section of our script. First, we set the frequency spacing to 1. With the modulation order set to 2, this results in 2 symbol frequencies, 1 and 2 Hz, representing symbols 0 and 1. We create a frequency vector to match the sampling rate. Then, we express each frequency as a change in phase using the cumulative sum function and create the final symbols vector by applying the exponential function. The code is ready to run. The figure shows the modulated signal, clearly representing 0 with a frequency of 1 Hz and 1 with a frequency of 2 Hz. And that's it for this video. If you want to explore more, be sure to watch the next video in the course, where I explain how complex numbers are used in DSP for constellation diagrams and the signal modulation process. Thanks for watching.